Okay, so now we're going to go ahead and discuss some aspects of chemistry and how those pertain to organic life. So, the substances of the universe, from a grain of salt to a star, are known as matter, which is defined by anything that occupies space and has mass. Elements are the fundamental substances that make up matter. Examples of elements include oxygen and carbon, among plenty of others that are listed in the periodic table of elements. These elements are in their pure form, meaning that they're distinguished from each other based on their atomic properties. The elements in the human body are shown in this picture, beginning with the most abundant, in oxygen, and then carbon, hydrogen, nitrogen, and then others. Each element's name can be replaced by a 1 or 2 letter symbol that you'll become familiar with throughout the course. All the elements that make you are derived from the foods that you eat and the air that you breathe. An atom is the smallest quantity of an element that retains the unique properties of that element. In other words, an atom of hydrogen is a unit of hydrogen, the smallest amount of hydrogen that can exist. Okay, but what exactly is an atom composed of then? An atom is made up of a nucleus that contains positively charged protons and neutrally charged neutrons, as well as negatively charged electrons that orbit this nucleus. The negative charge of electrons is attracted to the positive charge of protons, which keeps them from straying far and within a cloud. The number of protons and electrons within a neutral atom are equal, thus the atom's overall charge is balanced. Next, we can talk about some properties of elements like atomic and mass number. The atomic number is defined, the atomic number is determined by the number of protons in the nucleus of an atom, which determines the element of that atom. So, since an atom usually contains the same amount of electrons and protons, the atomic number also identifies the amount of electrons present in a given atom in its neutral state. The mass number is the sum of the protons and neutrons. In their most common form, many elements also contain the same number of neutrons and protons. Carbon, for instance, has 6 protons and 6 neutrons, providing a mass number of approximately 12. Electrons do have a little bit, but it's so negligible that we don't even count it. Carbon is a relatively light element. Uranium, in contrast, has a mass number of 238. It actually only has 92 protons, but contains 146 neutrons. You can always find out the number of neutrons in an atom by subtracting the atomic number, or the number of protons, from the mass number. So the periodic table of elements arranges elements in order of their atomic number and organizes elements according to their propensity to react with other elements, which we'll get into more when we discuss bonds. Although each element has a unique number of protons, it can exist as different isotopes, which are atoms of the same element that differ in number of neutrons. The standard isotope of carbon is carbon-12, or 12C. It has 6 protons and 6 neutrons, providing a mass number of 12. As all isotopes of carbon have 6 protons, thus carbon-13 has 6 protons and 7 neutrons. Another example can be hydrogen, which in its most common form has no neutrons and is called protium. The isotope of hydrogen with 1 neutron is called deuterium, and with 2 neutrons would be called tritium. An isotope that contains more than the usual amount of neutrons, including deuterium and tritium, are called heavy isotopes, and these are typically unstable and radioactive. Radioactive isotopes, nuclei, readily decay or break down, giving off subatomic particles and electromagnetic energy, which in large amounts are damaging to human and animal cells and plants, but in controlled amounts can be useful for diagnostics in modern medicine. So the controlled use of these radioisotopes can be used for advanced medical diagnoses and treatment of disease. They can be used to take images like PET scans, which is positron emission topography, to detect activity in the body of a very small injection of radioactive glucose, which are the simple sugars that cells use for energy. The PET scan reveals which of the patient's tissues is utilizing the most glucose and is thus the most metabolically active, such as in the case of cancerous cells that are hallmarked by uncontrolled cell growth utilizing high amounts of glucose as fuel. So these PET scans can help find cancer. That's kind of what this picture is showing, these radioactive blurs or blobs or cancerous cells that are radioactively labeled by that glucose that the person had put in them. Radioisotopes can also be used to destroy tissue, as in the case of radioembolization. They can't just put these radioactive elements or chemicals into the person's body because they can degrade other tissues, and so a targeted effect can be utilized to help destroy a tumor, such as using these radioactive particles to break up the tumor cells with high precision, and this helps just avoid destroying other tissues. So in the human body, atoms do not exist as independent entities. Rather, they are constantly reacting with other atoms to form and break down more complex substances. To fully understand anatomy and physiology, we're going to have to grasp how atoms participate in these reactions. The key is understanding the behavior of electrons. Although electrons don't follow rigid orbitals that we kind of have drawn out, they do tend to stay within certain regions of space called electron shells, which is the layer of electrons that surround the nucleus at distinct energy levels. The atoms of elements found in the human body have from 1 to 5 electron shells, and all electron shells hold 8 electrons except the first shell, which can only hold 2. You can kind of see that in this first electron shell with hydrogen and also with helium. The precise number of shells depends on the number of electrons in that atom, and hydrogen has only 1 electron while helium has 2. If you take a look at the periodic table, you will notice that hydrogen and helium are placed alone on either side of the top row. They're the only elements that have just 1 electron shell. A second shell is necessary to hold any more electrons in the elements larger than hydrogen and helium. Carbon, with its 6 electrons, entirely fills its first shell and half fills its second shell. So you can see the first shell is filled and the second shell has 4 out of the 8 that it desires. With 10 electrons, neon entirely fills its 2 electron shells. Again, a look at the periodic table will reveal that all of the elements in the second row, from lithium to neon, have just 2 electron shells. Atoms with more than 10 electrons require more than 2 shells. These elements occupy the third and subsequent rows of the periodic table. The factor that most strongly governs the tendency of an atom to participate in chemical reactions is the number of electrons in its valence shell. A valence shell is an atom's outermost electron shell. If this shell is full, the atom is stable, meaning its electrons the electrons are unlikely to be pulled away from the nucleus by the electrical charge of other atoms. If the valence shell is not full, the atom is reactive, meaning it's going to react with other atoms so that it can fill that valence shell. Consider hydrogen, with only 1 of its electrons in its outermost valence shell. This single electron is likely to be drawn into relationships with other atoms of other elements so that hydrogen's single valence shell can be stabilized. So basically, hydrogen's pretty reactive. In nature, atoms of one element tend to join with atoms of other elements in characteristic ways. For example, carbon commonly fills its valence shell by linking up with 4 atoms of hydrogen. In so doing, the 2 elements form the simplest organic molecules, methane, which also is one of the most abundant and stable carbon-containing compounds on Earth. As discussed before, another example is water. Oxygen needs 2 electrons to fill its valence shell. It commonly interacts with 2 atoms of hydrogen, forming hydrogen dioxide, or more commonly known as water. Incidentally, the name hydrogen reflects its contribution to water, hydro meaning water and gen meaning maker. Thus, hydrogen is simply the water maker. So, atoms don't physically come into contact, rather they utilize electrons to create various bonds like ionic, covalent, and hydrogen bonds. Bonds are weak or strong electrical attractions that hold atoms in the same vicinity, which typically creates stability for the atoms by fulfilling valence electron shells. This grouping of atoms together, held together by a chemical bond, is called a molecule. Bonds of two or more atoms of the same element create molecular elements such as molecular hydrogen or oxygen. If they're with other atoms of different elements, then these create chemical compounds such as water and carbon dioxide. So before we really dive into ionic bonds, we really need to discuss what an ion is, which is an atom with an electrical charge, either positive or negative. An atom becomes an ion when it loses or gains an electron from its outermost shell, or the valence shell. And an ion that has lost an electron now has more protons than electrons, thus is positively charged, and is called a cation. An ion that has gained an electron now has more electrons than protons, thus is negatively charged and called an anion. These ions act as electrolytes that are important in physiology. An ionic bond is formed when the opposite charges of these ions exert a moderately strong mutual attraction that keeps the atoms in close proximity. This will typically be seen in metal atoms that readily transfer electrons to become metal ions. This ongoing close association can be seen in sodium chloride, commonly known as table salt. Elemental sodium, which reacts with water violently, donates an electron to chloride, bing, which reacts with the chloride or the chlorine molecule becoming chloride now. And now that chlorine is fulfilling that outermost shell, it is more stable. So the sodium ion lost an electron in its outermost shell, so it's stable. The chloride ion lost it or gained an electron in its outermost shell, and now it is stable. These are non-reactive now, and they can be sprinkled on your fries. Water is an essential component of life because it can break these ionic bonds in salts to form free ions in the solution. Most biological fluids don't consist of individual atoms like sodium and chlorine, rather ions of those atoms, such as the sodium ion and the chlorine or the chloride ion. And we'll see those a lot, especially when we start talking about the nervous system. These dissolved ions produce electrical charges within the body and are crucial to physiology. Next, we can take a look at covalent bonds. Unlike ionic bonds formed by the attraction between a cation's positive charge and an anion's negative charge, molecules formed by a covalent bond share electrons in a mutually stabilizing relationship. The atoms do not gain or lose electrons permanently. Instead, the electrons move back and forth between the elements in that outermost shell. Because of the close sharing of pairs of electrons, one electron from each of the two atoms, the covalent bonds are actually stronger than ionic bonds. If you've ever had a chemistry class, they'll tell you the opposite. They'll tell you that ionic bonds are stronger. It's true, they are stronger, but covalent bonds in human physiology are stronger because they are not actually, ionic bonds are not actually present as ionic bonds. They're present as ions. They're not actually linked together. All the fluids in the body have water in them, dissolving these ionic bonds into ions, so they're not actually bonded. The covalent bonds are going to be stronger when we're talking about human biology. The important concept to take away from this is that covalent bonds, the electrons in the two atoms' overlapping atomic orbitals are shared to fill the valence shells of both atoms, ultimately stabilizing both of the atoms involved. In a single covalent bond, a single electron pair is shared between two atoms, while in a double covalent bond, two pairs of electrons are shared between two atoms. There are even triple covalent bonds where three electron pairs are shared between two atoms. This will most commonly be seen in non-metal atoms on the right side of the periodic table. The weakest bonds are hydrogen bonds, which form between hydrogen atoms and nearby oxygen or nitrogen atoms. We can see hydrogen bonding in water, giving it its surface tension and keeping it together, as well as in DNA, providing bonding between nitrogenous bases. And these are very easily broken bonds, very weak. So out of the three of them, they're definitely the weakest. So far we have covalent, ionic, and then hydrogen bonds when it comes from strongest to weakest for bonds in human biology terms.